Today I'm comparing both lanthanides and actinides. Okay, already we know both are related to a block. So in these block elements, the electron enters into anti-penultimate shell. Anti-penultimate shell means here N-2 F orbital. Okay, you can clearly observe this electronic configuration. You can see outer shell is called ultimate shell 6s2, and next to the outermost is the penultimate shell. Okay, next to this shell is called anti-penultimate shell. Okay, so these two lanthanides and actinides, the electron always enters into anti-penultimate shell. So coming to the lanthanides, in lanthanides the electron enters into 4f orbital. In actinides the electron enters into 5f orbital. So hence it is called 4f series. In actinides we call them as a 5f series. So lanthanides are the naturally occurring elements actually, but in actinides we can observe some elements are man-made or synthetic elements. We call them as artificial elements. That means I can give you best example as uranium, which is a synthetic element or man-made element. And now let us see the comparison between oxidation states of both lanthanides and actinides. So oxidation states, already we know lanthanides common oxidation state is +3, but there are some elements which can exhibit +4 and +2 also. Best example I can give you cerium. Cerium atomic number 58. If you write the electronic configuration, we'll get xenon 4f25d0 6s2. So cerium +4, on losing 4 electrons it will become xenon, noble gas configuration. So it loses 4 electrons and exhibits +4 oxidation state. Okay, next we can observe this one, europium and ytterbium. Both will exhibit the +2 oxidation state. Europium, if you take, we can write xenon 4f7 5d0 6s2. Okay, if we remove the 2 electrons, it will become xenon 4f7, that is half filled electronic configuration. Same way ytterbium, if you write, you will get xenon 4f14 5d0 6s2. If you remove 2 electrons, it will become 4f14 in case of ytterbium. So in case of europium, it will exhibit half filled configuration in 4f orbital. In case of ytterbium, it exhibits fully filled configuration in 4f orbital. So in order to attain half filled and full filled configurations, they'll exhibit +2 oxidation states. And next, coming to the actinides, common oxidation state of actinides is +4 or +3. Okay, americium, but there are some elements in this also exhibits +2, and they'll exhibit highest oxidation state, that is +7. So americium and nobelium exhibits +2. I'm writing americium electronic configuration, atomic number 95. If you write this electronic configuration, radon 5f7 6d0 7s2. And nobelium, if you write 102 atomic number and radon 5f14 6d0 7s2. Okay, they lose 2 electrons to get half filled and fully filled configurations. Hence they'll exhibit +2 oxidation states. Next, coming to the highest oxidation state of the actinides. Highest oxidation states exhibited by both neptunium and plutonium. They'll exhibit +7 oxidation state. So if I write the neptunium, I'm giving you the example here. Neptunium atomic number 93. If I write here electronic configuration, you'll get radon 5f14 6d1 7s2. Okay, so it will lose. Okay, radon 5f4 6d1 7s2. It will lose all these 7 electrons. It will become radon electronic configuration. That is noble gas radon. It will exhibit +7 by losing all electrons. It will become noble gas configuration. Similar way, but plutonium loses only 7 electrons and exhibits a +7 stable gas configuration. To the magnetic properties. So already we know magnetic properties means here we'll discuss about paramagnetic and diamagnetic substances. Okay, so in case of lanthanides, except lanthanum La+3 ion and lutetium +3 ion, remaining all exhibits paramagnetic nature. So if you observe the lanthanum, lanthanum +3 means we'll remove these 3 electrons, it will become xenon. And lutetium +3 means we'll remove these 3, it will become completely filled 4f subshell. That means it is both are not having unpaired electrons. So they are not having unpaired electrons means they are not paramagnetic substances. They comes under diamagnetic substances. So paramagnetic substances will show the magnetic character. Okay, so by using this formula we can calculate this magnetic momentum. Mu equals to √4s into s+1 plus L into L+1. Okay, we are adding both spin angular momentum and orbital angular momentum for the calculation of the magnetic momentum. But in case of actinides, this orbital angular momentum is quenched. That means it's not considered. Why? Because 5f orbital is far from the nucleus. Okay, 5f orbital is far from the nucleus, hence nucleus shows less attraction on the 5f electrons. So hence we are not considering this orbital angular momentum. Only we will consider spin angular momentum in case of actinides. And next, coming to the atomic radius. Atomic radius or ionic radius is same, and now atomic radius means we have discussed in lanthanide contraction already. Lanthanide contraction means what? The slow decrease of size from left to right of lanthanides is called lanthanide contraction. In case of actinides, what we'll call this as actinide contraction. Okay, actinide contraction is nothing but steady decrease or slow decrease from starting element to the ending element of actinides is called actinide contraction. Okay, so this actinide contraction is similar to the lanthanide contraction in the initial stage. But as the elements are moving from left to right, from curium onwards, it becomes smaller than expected. Okay, smaller than expected. This is mainly due to the poor shielding effect of 5f electrons. This 5f electrons cannot shield the nuclear attraction on the valence electrons. Hence, because it is far from the nucleus, and already I told you, f orbitals will have a diffused shape. They are not having a particular shape, so they cannot shield the electrons. When compared to 4f electrons, 5f electrons will show less or poor shielding effect. Because of this, from curium onwards, this actinide contraction becomes small. Coming to the comparison of color properties. So the color properties already we learned in the case of transition elements. The color is due to the presence of unpaired electron. Not only unpaired electron, the transition or movement of unpaired electron between the energy levels. Due to that transition, we'll get the color. Okay, so here the lanthanides also exhibit the color due to the presence of unpaired electron, and this is due to FF transition. The transition between F orbital and another F orbital gives the color to the particular element or particular salts. So here this transition also depends on the particular visible region. So whenever the electron is moving from one level to another level, it absorbs energy. Okay, it absorbs particular energy and transmits the energy which is opposite to the particular color. Okay, due to that we are getting color to the particular substance. So here visible region, already we know VIBGYOR, VIBGYOR, VIBGYOR region. So different colors will be present in VIBGYOR region. Basing on that particular colors, we will get the color to the particular salts. Here lanthanum is lanthanum plus 3 ion is having 0 electrons, unpaired electrons, so it is colorless in nature. And neodymium is having neodymium plus 3 having 3 unpaired electrons, it is exhibiting red color. And promethium is having 4 unpaired electrons, it is exhibiting yellow color. Okay, this color is not only depends on unpaired electrons, it also depends on the absorption energy, the required absorption energy in the visible region. Okay. Next, in case of actinides, the 5f0, 5f7 containing elements are colorless. 5f0 already stable, empty orbitals are already stable, they won't show any transition, and half-filled orbitals are also stable because of equal symmetry, and completely filled orbitals also stable, they won't exhibit color in case of actinides. Remaining all elements will show this color. Okay, next coming to the complex formation. So complex formation means, already I told you, when complex here is a formation between both metal and ligand, and they'll give the coordinate covalent bond. Ligand donates electrons to the metal and exhibits the stability in order to form a coordinate covalent bond. Here lanthanides also shows this complex formation, but they'll show moderate tendency. Why? Because the 4 electrons in lanthanides are shielded by the 5d and 6s electrons. Because of that, it shows less tendency to form complexes, but it shows the more tendency with the less small sized ligands. So F minus, Cl minus, H2O, OH minus will form complexes easily with ligands, and EDTA. So complexing chelating ligands like EDTA will form a ring-like structure around this lanthanides to exhibit the stability. stability. Okay, in case of actinides, actinides shows more tendency when compared to lanthanides because of their very small size when compared to lanthanides.